Sorry to go quick, but it's chapel day, so we need to get headed. Kiddos, we have this in our notes from Friday, because yesterday was Monday. How were you supposed to find the slope of the graph at the point? What did I do yesterday in notes? Just walk me through it real fast. I plugged in the x value to what? Into the formula. Good. Not point slope yet. That's coming. So I have the limit as, we're using h's, right? C plus h minus f of c. I actually plugged in the x all the way through, right? So where are we trying to find the slope, aka the derivative? The slope of the tangent line. Lots of vocab for what we're doing. It's all pretty much the same process. How do we find the slope? Well, what x value are we trying to find the slope at? -2. So we can say f prime of -2. That's shortcut notation for the slope of the tangent line, aka the derivative at -2. Plug in -2 for each of the x values. We're literally using the formula up above. Okay? Where we say, hey, if we want just one slope, we can plug just one slope, that special x value in all the x spots. Now, the name of the game is solve the limit. But in order to solve the limit, well, hold on. Wait a minute. Don't I have to somehow resolve the idea that I have these f of x's down here and I have this f of x up here? How do I resolve that? How do I actually get the function plugged in? Yeah, plug it in, plug it in. Plugging in what? The new input argument. The new input argument. The old argument was x. What's the new argument? -2 plus h. So we're going to go ahead and say, okay, the derivative or the slope at this point is going to equal, instead of x being squared, what's going to be squared instead? Yeah. Making sure my sound is off. There it is. So instead of instead of x being squared, -2 plus h is being squared. How about for the next one? What's the new argument now? -2. So instead of x being squared, it's going to be -2 being squared. Once again, I have to look back to my function and say, hey, the function says square the input. So square -2 plus h and square -2. Okay? Now, if I was to plug in right now h equals 0 to any difference quotient, which is of the form f of x plus h minus f of x all over h, it's going to be 0 over 0. But what does that tell me?
Keep going.
Okay. Yeah. So, someone, not even in this problem, tell me a way to keep going for a limit. What's the first way we usually try? Factoring. Then maybe polynomial division if we don't like the factors. But what if that doesn't work? Maybe there's a radical and I multiply by the...
Oh, reciprocal.
No, not reciprocal. What's it called? You change only the middle sign? Conjugate. Multiply by the conjugate. But there's no radical in this one. Maybe there's a complex fraction and we simplify. No, but simplify. What can we simplify? Foil. We can totally foil. So if we foil the top, I'm going to go quick because you guys already had me going slow yesterday. That'd be 4 minus 4h plus h squared. If I square -2, that's 4, so I have minus 4. What did you guys notice yesterday when I went to simplify after foiling in?
You can get rid of the 4 and the 4.
I can get rid of the 4 and the -4. And what does the top have in common? I think Karina was saying that. There's an h in common that you can factor out. And when you factor out the h in common, then there's an h on top and there's an h on bottom. It's technically not called canceling. What's it called? Reducing. I heard someone say it. Reducing. And then, wait a minute, I've been rewriting this little limit. He's been tagging along the whole time because what do I need to remember right now to finish? Plug in 0. And what's -4 plus 0? Because I plug in 0 for h. -4. So what is the answer to the slope of the graph at the point? -2, 4. -4. Now, on the video yesterday, did I go into my graphing calculator and show how to use the derivative feature? No.
I don't remember.
I think I might have done that a different day. I want you guys to grab out your graphing calculators really cool. Let's take a derivative on our calculator for, is it the first time for us this year? Have we done this yet? No. Yeah. All right. Well, let's go to our calculators and let's see how our calculators can actually help us with this. Now, Like in all math, you can't always do everything on the calculator. The only thing the calculator can do as far as derivatives is find the slope of the tangent line at a point. It cannot find the derivative function which has x's in it. It can't find the derivative function which still has x's in it. But it can find the numeric value of one slope at one point if I know what the point is. Now, do you guys see how I have x squared in my calculator? It's like it's just ready to go. I have x squared in my calculator. If I get a graph of x squared, could I find the point fairly quickly? Actually, no, I didn't hit that. Can I find the point at -2 pretty quickly? You can do second trace value, or you can just hit the trace button and type -2. It's a shortcut. It's kind of cool. I have the point -2, 4, but question, do they want the x or the y at this point? No. What do they want? Slope. And since this is not a line, is it the same slope as everybody else on this page? No. How do I think about the slope of this one point?
You have to have a line.
The line tangent.
A line that skims a tangent. So can we actually, if I could do this and it would work, could I draw a little line and be like, that's about it?
Theoretically,
Yeah.
yes.
But how do I find the number, the numeric value?
Find
That thing.
This, which worked. Or I could have done this with, instead of -2 plugged in, I could have done it with x's plugged in. At the end of the day, we would have actually gotten 2x at the end. And then we would have plugged in -2, and 2 times -2 is -4. We did it so that we only got a number at the end, and we plugged in at the beginning. Now, if I hit second calc, didn't there used to be super cool things that we could do?
There's
Value
Yes.
0, minimum, maximum, intersect. What's number 6? dydx is a spiffy notation that one of the creators, actually the second one, kind of got it wrong, and the other guy had to come and kind of correct him. He came up with this thing called Leibniz notation, and his notation brought this little d in to signify differentiating. It's called a differential. It's a lot deeper than that, but for right now, we'll just say this has something to do with the derivative. Think of it as change in y over change in x, but it's not change in y over change in x of a function. It's change in y over change in x of the tangent line, and you put a little d in there in order to say, hey, this is the derivative. This is for the tangent line. Anyway, long story short, hit number 6. Nothing happened. Wait, don't we always have to type in an x value to tell it where we want it? If we type in -2, I wonder if -4 will pop out. Ooh. That's kind of spiffy. So the derivative of this curve at -2, it can find me a number. It can't find me a function. It can find me a number. So I was able to check and see that. Right. There's actually another way. I can't use my smartboard. Come over here. Hopefully it's fixed by next year. We can maybe be praying in the back of our minds for that. Isn't there also cool stuff in the math menu? Go up. Does anybody see number 8? What does that look like?
And derivative.
Derive? Like derivative? It has all of its own like conjugations for differentiate and differentiable and derive and derivative and different.
There's a lot of
I don't know. There's a verb.
No.
There's a noun.
Adjective.
Is there an adverb?
Adjective?
There's an adjective,
No.
differentiable, but it's kind of like a weird variation. Anyway, hit number 8. Ooh, what's going on here? Wait a minute. Huh. In parentheses, I want x squared to be the function. ddx is something that most of you wouldn't have naturally thought of. If you think about dy dx thing, well, on the bottom was a dx. ddx is the verb, dy dx is the noun that says, hey, let's take a derivative. And if you come over here, that straight up and down line we've seen a couple times in math this year, but you probably forgot it. It's called such that. And the such that says, oh, hey, you told me x, so which x do you want? And I say, oh, -2, please. Dun, 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 dun.
Oh, sweet.
All different ways of taking derivatives.
That's fun.
But I'm sure you guys too much already. Let's get back to our pre-cal stuff. That's more calculus, man. And you guys have one up for next year. All right, so boop, boop, boop. Let's keep going. You guys also did an example on this page. Long story short, we already talked about the derivative is the snazzy name for slopes of a curve, which are slopes of tangent lines, which are instantaneous rates of change. We already crossed all this stuff out because it's like, well, right already. We already wrote all this stuff down. So let's just go do it. Except, I think right about now, is it right about now, Tyler? I brought in this little shortcutty thing that maybe if you stick around, next year you'll learn. There is a way to solve this with f prime of x equaling and the difference quotient, which we've been talking about, the limit as h approaches 0, of f of x plus h minus f of x all over h. And I am going to show you how to do that because that is the point of chapter 12, basically, is giving you a basic understanding of limits, which is what we build off in or off of in calculus. But I also want to show you a peek of calculus, and so I'm going to say, you know what? Even though these limits are really good and they do give you guys the idea of what's going on, a tangent line is impossible to find without a limit, the limits of secant lines, there are these shortcuts in calculus that let us take derivatives of x's to powers. And I'm going to make this a little bit more general and say, you know what? We can even deal with a number in front if there is one, and we'll call that number c for a constant. And the power rule says in calculus that in order to take the derivative of a piece with a number times an x to a power, and this is just one of many shortcut rules, you can bring down the power, think of it as this little guy coming down, bring down the power, the c is just chilling, the x is still there, but his power just got decreased by 1. Now, in the last page, I did mention this quite briefly, and I think it was earlier. But if we were going to take the derivative, which was the last example, the derivative, remember this is the verb, of x squared. Now, we wanted it at x equals -2, but for right now, the derivative of x squared. How would we use the rule that you guys see up above, right up here? Bring down the 2, so the power comes down, out in front. Bring down the 2. There's no number in front of x, so whatever. And what happens to the new power of x? It gets decreased by 1. So my derivative is now 2x, because 2 minus 1 is 1. This is f prime of x, but remember in the last problem we wanted f prime of who?
-2.
So what do you do if you got to plug in? Well, you plug in.
-4.
Is that a little easier than that whole limit that we did?
Yes, very well.
Ooh. So let's just say, hey, maybe we'll pretend that we know calculus, at least the shortcut rules. Let's look at this example real quick. And before we do the limit, which I'm going to do, and I'm going to do it really fast, before we do the limit, if you guys can learn the power rule, maybe you can shortcut a few things on maybe a question. How would you find the derivative? And I know I'm not teaching you all the rules and all the ins and outs, but long story short, you can do it piece by piece. So I'm going to put a big old subtraction in here and say, let's look at the first term, then let's look at the second term. How would you take the derivative of 3x squared? What do you think?
Bring down 2, multiply by 3.
Bring down the 2. Say it this way. Bring down the 2. Keep the 3. The power of x gets decreased by
1.
1.
So that would be 6x.
Yep, we're getting there. Hold on. Minus. What's the derivative of 2x? What's the power of 2x?
1. So then
Good.
2. 1.
So bring down the 1. Keep the 2. And what happens to the power? Decreased by 1. Just following the power rule off to the side, the one that I'm kind of cheating and letting you see early. So then some people already started to simplify. 2 times 3 is 6. X to the 2 minus 1 is just x to the 1 minus 1 times 2 is 2. What's x to the 0?
1.
Anything to the 0 power is 1. So this is what we think the derivative is from the power rule. So let's see if the limit formula gets us the same thing. It should. So we're going to go ahead and say, hey, what's the input of our function? X plus h and then x. And our function is, there's multiple inputs up there. 3 input squared minus 2 times input, or 3x squared. So in order to solve our limit, we're going to have to go ahead and This is what you guys should have seen yesterday.
You did.
Absolutely.
3 input squared minus 2 times input, so I have x plus h, minus, my f of x is just 3x squared minus 2x, all over h. Guess what happens when you plug in?
It goes to 0, 0, so that means
Eventually
you have
it
to go.
becomes 6x minus 2.
What? That's what we hope.
That's what I would.
That is what
That's
happened
what I know.
yesterday, or it should have happened yesterday,
Yes.
because as you FOIL things out, just to remind us of the process though. So I might give you a limit problem and not call it a derivative, and then you just kind of have to go for it and not use the cool trick. We end up with 3 times x squared plus 3 times 2hx, which is 6hx, plus 3 times h squared minus 2x minus 2h minus 3x squared plus 2x. What ended up happening to all those non-h terms in the numerator? Cancel, 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 cancel. What does everybody who's left have in common?
They look kind of like that.
An h. And so if I pull out a common h, I have 6x plus 3h minus 2 all over h. What's that word called when I can cross out numerator denominator when they're
Oh,
shared?
so reducing.
Reduce. And what's my last step to solving the limit, which is why I've kept on writing it?
Add the h.
Plug in, h is 0. So what's 6x with an h plugged in? Still 6x. What's 3h with an h of 0 plugged in?
0.
0. And then what's minus 2 with an h plugged in? Hey, did they work? Did they check? Are they the same thing? Which way did you like better? That's the real question.
I like the one that was easier.
First way is good. You just kind of have to learn it, huh? Oh, because I have to plug in h is 0. So the 3h cancels. Remember, when we're doing limits, we have to finish off by plugging in. And since it was an h, we plugged in. There you go. Is that better? So then that cancels to 0. And all we have left is 6x minus 2. So let's test this out just really, really, really fast. Do you guys still have your calculators close? What if I was to, what do you guys like better, the home screen one or the graph one?
The graph is very neat and laid out.
Home screen one.
Home screen one seems faster, right?
Yeah.
Okay, so let's get to the home screen one. Let's, where do you guys want to find the derivative at? Because we're just going to kind of check and see if this seems right.
15.
15? Okay, that sounds fun. So we'll plug in 15. You guys going to do the mental math? What's 6 times 15? 3 sets of 30? 90 minus 2, is that 88? Someone check me. Come on, don't trust me.
6 times 15?
Yeah.
That's 30. 90.
And then minus 2?
That'd be 88.
You don't have to plug that into your calculator.
I did it!
So much judgment right now.
Yeah,
It's all coming from Ricky, just saying.
That's the first thing I said all class period.
that's
All right,
true, actually.
pause and
He's
quiet.
oh,
According to the formula, 6 times 15 is 90 minus 2 is 88. Let's see if the calculator agrees with the derivative of the original at 15. Dun, 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 dun. Dun, dun. So the calculator cannot find you the derivative formula, but it can check like a numeric value. You can kind of see if it seems like you got it right. All right, cool kids. We did have other examples from yesterday. I'm not going to go too crazy in. Let me show you like on the notes online real fast. I'm going to make sure they're all saved for you. We did do another example. I think I introduced the power rule a little bit more, like I actually did the power. Oh, I talked about it. Then I did an example from the book number 13. Then I did an example from your homework exercises number 61. Hey, did I even do a limit in 61? Nope, I totally was like, so the power rule is fun. Let's do that instead, because who wants to cube a polynomial? Anyway, Pascal's triangle. There is one thing. I'm going to make sure that all that's saved in your notes online, because that is in the video that you were supposed to watch from yesterday, and some of you guys can then access it if you were gone yesterday. But there, I think, is one example that we haven't done yet that's pretty important. Then we'll introduce section 12.4. Finish it tomorrow. We're going straight to a quiz, quest, whatever you want to call it, on Thursday. So, if you guys have questions on 12.1, 12.2, 12.3, come in, because you're not going to have like a full review day like we used to. So I want to start reviewing on Friday. Then we have Friday, Monday, Tuesday, Wednesday to review almost a full week. Talk about formula cards and all that stuff. All right, cool kids. This is the one thing that I didn't go over yet. But how unfamiliar? Well, how many times have you seen point slope in the past? Some of you were like, "Yeah, I never really
Sixth
done it."
I
grade.
can't count it.
Oh yeah, it's 6. I think it's like algebra 1, maybe. Anyway, this equation shouldn't be super crazy, like, oh my goodness, it's brand new. But we're not just finding the equation of any line. What are we finding the equation of?
Tangent.
We have a point.
So if you are, and this is what I tried to show you yesterday, if you are given x equals c. Now, if they give you an x and a y, perfect. You know x1, you know y1. It's great. But if they just give you x equals c, then how are we going to make this tangent line equation particular to that c? Now, there's one more thing actually they're going to have to give you. They're going to have to give you x equals c and a function. Some sort of function to work with. Otherwise, well, who knows what you're finding the equation of a line to. All right. When I'm plugging into the point slope form, there's always a y and an x that's left over. I keep plugging x1, plugging y1, plugging n. Yeah, we're done. Y equals mx plus b. So there is going to be a y that stays. And there's also going to be an x that stays. There's going to be a y that stays. There's going to be an x that stays. Now, where is c going to go? Yeah, where the x1 is. Good, good, good. The c is an x value. If you have an x value and you have a function, how can you find the y value? Oh, plug it into the function? So I could replace y1 with what? But f of x when x is c. Good. Now here's where the real new stuff comes in. Is it really all that new based on what you've seen the last couple days? What am I going to plug into the slope of the tangent line equation? And the notation for derivative is f apostrophe, but we call that apostrophe in for a prime. F prime, but not of x, because x is 2. I need a specific x and a specific y and a specific derivative. A number for x1, a number for y1, and a number for the derivative also. So whenever you see in your homework, if you haven't finished 12th grade for today and you're going to be finishing it tonight, something to do with the equation of the tangent line, this is the formula you're going to be using, and I'll make sure to get those examples, those extra examples you guys did in the video yesterday. Get those written down so that you can use them. Sound good? So, question, is the power rule officially in this section?
No.
Could it make things a lot easier?
Yes.
And or give you a way to check some really tricky limits? Yes. Okay, we're not done yet, but we are in section 12, please.
Yay.
Gosh.
12.4, the last thing that I want to show you this year. Quite literally. 12.4, the last thing I want to show you. We have talked about limits using tables, using graphs, using algebra. We've talked about easy ones, where the two-sided limits agree and thus the limit exists. We've talked about harder ones, where the two-sided limits do not agree and thus the limit does not exist.
Yeah.
Two-sided limits do not exist. So the limit does not exist. We talked about crazy limits, how when you come in towards a constant, instead of going towards a set height, even if they don't agree, or if they do agree, maybe they can go to infinity, the function, or negative infinity. We talked about when those agree, and we say infinity or negative infinity. Or when they don't agree, so we say the limit does not exist. So we've actually talked about vertical asymptotes and limits towards vertical asymptotes. But what have we not talked about with limits? Horizontal. And what have we not talked about? Limits. What if you're going to infinity and not to a constant? What if you're going to infinity? Not to the constant. Graphically, you guys look at that thingamabob. My question to you is, does it have a horizontal asymptote?
Yes.
Yes. Where?
At y equals 1.
At y equals, why did you say y equals, not x?
Squared, so horizontal.
Take a mark on the y-axis, right? It's a horizontal line. So yes, there is a horizontal asymptote at y equals 1/2. But can I show you what this also means? There is a horizontal asymptote at y equals 1/2. Looking at the graph, we see it. It's the function as you go to the right, it's decreasing towards the horizontal asymptote. As you go to the left, it's increasing. Yes, there is a horizontal line. The function is getting closer and closer and closer too. But there's another way of writing horizontal asymptotes. And it's actually what they are at their core. We talked about earlier this year the end behavior of a graph. Does anybody know how I describe end behavior of a graph? As the x's go to positive or negative infinity, what are the y's doing? And we even learned the little arrows way back then, the approaching arrows. So what allows us to have x's approach something? But what's new is that we're going to say the limit as x approaches infinity, it's not going, the function, the x is no longer going in towards a constant. We're going to end here by saying limits x's can also go to the right or to the left, to positive infinity or to negative infinity. So I could say the limit as x goes to infinity is 1/2, and in this case, which is not always true, ironically enough, I'll show you a funny function maybe tomorrow that's not true. But in this one, you can also say as x goes to negative infinity, the function is 1/2. So at the beginning of the year, when I first taught you the arrow, in my mind the whole time, it was right now, and I would teach you how that corresponds to a limit. And I might have even said something way back when, but I doubt anyone can remember that. Because the whole idea of the arrow, the whole idea of learning the terminology of the arrow, the approaching, was to build up to the limit. But here's the crazy thing. Well, you guys said you've seen horizontal asymptotes before, right?
Sure.
And haven't we learned ways of talking about horizontal asymptotes? So maybe how to solve limits to infinity use the same ways as horizontal asymptotes? Maybe it's not really that new. Maybe the solving isn't new. Maybe just realizing what you're truly solving for is new. So the crazy thing is the end behavior of a function is the same thing as x approaches infinity and as x approaches negative infinity, which sometimes agree with each other, but sometimes they don't. What we saw earlier in the year, as x approaches infinity, what is f of x doing? And as x approaches negative infinity, what is f of x doing? This was a perfect lead-in to limits. Because limits answer the question, what are the y's doing as x's approach? So, the idea is, how we've learned and even how we informally define limits was x is approaching a constant from below and from above. X is coming towards a constant. But the problem is we have to redefine and say x does not always have to come towards a constant. X can also increase without bound and decrease without bound. And we need to say, what are the y's doing? What are the y's approaching, if anything? If anything. So for instance, if I was to give you something like the limit as x approaches infinity of x cubed. Does anybody have a way of thinking about that problem? The limit as x goes to infinity of x cubed. I see someone pointing. I think they're trying to have me say we should look at the graph of x cubed. What's the graph of x cubed?
That's
Oh, yeah, that's
They're opposite ways, right? Opposite ways. Is that help us at all? Try to think about the limit as x approaches infinity if the basic graph looks like this. What are the y's doing? I decided. Where are the y's going as x pushes to positive infinity, which means as we're headed to the right. We're not coming from the left, from the right. We're just going, sorry, from your perspective, we're going towards the right. So look at the function, that's cubed. As I go towards the right, what's it doing? Increases without bounds. So how would we explain that in an answer?
Up there with the smiley face.
No, Caleb.
Infinity! Now, how would we answer, though, the limit as x goes to negative infinity?
With a negative infinity, the smiley face.
Because what's going on as the graph goes to the left?
It's going down forever.
So tons of functions don't have horizontal asymptotes. Tons of functions are just going, like all polynomials, because x squared, x to the fourth ends up that way, x to the x cubed, or x to the fifth, right? And then it could be going negative or positive. You guys remember that kind of from the beginning of the year. We had a little dance moves as far as what was going on with even or odd polynomials. But there are certain functions that don't increase without bound, decrease without bound as you go to the right to the left. And those are the special ones for horizontal asymptotes. So, to redefine, not even redefine, why are you throwing things? To talk about, well, how do we deal with these limits at infinity? We just say, okay, we have to kind of redefine a limit. And just say limit to it. We can go not only in towards the constant from below and above, but also go to the right and to the left. We just change it up a little bit. Just say if you're taking a limit, they say at infinity. I don't like that terminology because you can't actually be at infinity. I'd rather say to infinity.
Beyond.
Yeah. Either way, we can say a limit at to infinity will exist if the value of f of x gets arbitrarily close. It gets closer and closer and closer by this to a certain constant as x increases or decreases without bound. And some of you already said the idea increases without bound is x approaching positive infinity, decreases without bound, x is approaching negative infinity. And there's a quick little note saying the two do not always agree, sadly. I'm going to give you a quick example. And this is one that, to be honest, lots of calculus kids get mixed up. I'm going to show it to you now. What if I was to give you something with 7 minus 3 to the x all over. Let's do 1 plus 3 to the x. We'll look at this guy at the beginning of tomorrow. He's not quite the normal, hey, which degree is stronger type problem. We're going to see why he's a weird one. So, I do believe. What we're going to look at tomorrow, kiddos, is basically reviewing horizontal asymptotes in the same way. If it's a fraction, who wins, top or bottom? If it's not a fraction, how do we deal with it? And if it's not a top or bottom that we're used to, how do we deal with those? But for the most part, if you guys want to brush up on horizontal asymptotes that you were supposed to yesterday, and probably don't need to do. Peek back horizontal asymptotes in your notes from, someone look this up, chapter, I don't remember, we were talking about vertical asymptotes and holes and horizontal asymptotes, all the same section. Go peek at those, the degree tests what we're going to review tomorrow. And then, what do you have to have finished by tomorrow?
Homework.
Homework 12. Okay? Alright, get on here, I'll let you go. 10 seconds early.
Have a great day, Miss Julie.
Be good, don't be trouble like the ones who were just in the hallway.
Thank you. We'll try not to.
Jason.
Good job, Julie. Good job.
Thanks, you too.
Mistake.
Bye, Nathan.